Welcome to the today's session of the subject electromagnetic waves and transmission lines. In this session, we are going to start a new chapter, that is chapter 2, and whose name is magnetostatics. Unlike in unit 1 where we have electrostatics, here we have magnetostatics. So in first and second unit, there is one particular part which is repeated, statics. Unit 1 electrostatics, unit 2 magnetostatics. What is electrostatics? The study of static electric fields. Similarly, what is magnetostatics? The study of static magnetic fields. However, in real time, the wireless communications is based on dynamic electric and dynamic magnetic fields, which are time varying electromagnetic fields. However, before going to understand or master the time varying fields, it is essential for us to understand them in static domain, time invariant domain. Hence, two chapters are dedicated, one for static electric fields, which is electrostatics, and the second unit for static magnetic fields, which is magnetostatics. Now, there are several parameters associated with magnetostatics, which we say magnetic field, magnetic flux density, magnetic susceptibility, magnetic permeability, magnetic force, magnetic inductance. There are many parameters, but the magnetostatics, the study of magnetostatics starts with two important parameters. Number 1, magnetic field. Number 2, magnetic flux density. So here are the two topics, which is starting with magnetic field. Of course, we are dealing with intensity, the magnetic field intensity, and the second one, magnetic flux density. Now, we will see first what is magnetic field intensity. As you know, the word intensity indicates or tells you about how strong a particular parameter is. That's why we say intense. The word intense or intensity indicates how strong. It's a measure of how strong or weak a parameter. In this case, it is magnetic field. So what it tells you? It's a measure of either the strength or weakness of the magnetic field. Now, what is magnetic field? It is nothing but the amount of force. Force means magnetic force, because we are dealing magnetostatics. When I say field, it is magnetic field. When I say flux, it is magnetic flux. When I say force, it is magnetic force. They should be prefixed with the word magnetic. So what is magnetic field? It is the amount of magnetic force which is experienced by a unit north pole, which is of unit strength. Unit means, because we express the pole strength, magnetic pole strength is expressed in terms of Webers. So unit north pole means 1 Weber strong, 1 Weber of north pole strength, how much it is experiencing a magnetic force. Because in electrostatics, we have duals, positive electric charge, negative electric charge. But this is magnetostatics. Instead of positive and negative, here we have north pole, south pole. Whereas in electrostatics, we have positive charge, negative charge. That's the difference between unit 1 and unit 2. And to proceed further, the electric lines of force always start at positive charge, end at negative charge. Whereas magnetic lines of force start at north pole, end at south pole. That's the difference. If you take a magnet, we have north pole and south pole. Magnetic lines of force will start at north pole, end at south pole. This is outside the magnet. If you take inside the magnet, it goes from south to north. So like we have positive and negative electric charges in electrostatics, we have north pole and south pole in magnetostatics. What was the definition of electric field? The amount of electric force exerted on a unit electric charge. Same thing here. What is magnetic field now? The amount of magnetic force exerted or experienced by a unit magnetic charge. There we take positive charge, here we take north pole, because their electric lines of force start from positive charge, here magnetic lines of force start from north pole. That's the only difference. So magnetic field is the amount of magnetic force experienced by a unit magnetic charge. Unit means 1 Weber, because magnetic charge is expressed in Weber. Like electric charge is expressed in Coulomb, magnetic charge is expressed in Weber. This is the definition of magnetic field. Now, how do you get magnetic field? There are two ways. Of course, it's not just magnetic field. The question is, how do you get static magnetic field? Because it is not magnetic field, it is magnetostatic field. That's the title here. That is written here. Magnetostatic means it's not just the study of magnetic fields. It's the study of static magnetic fields. Now, immediate question is, how do you get such static magnetic field? Well, there are two ways you can get static magnetic field. One, with a magnet, and the second way is with a current carrying conductor. This is a conductor in which or along which current is flowing, and you know a current carrying conductor is surrounded by magnetic field. Of course, what is the direction of magnetic field? That's a different thing. That will depend on the direction of current. But the important thing is, when electric current flows through a conductor, it is surrounded by magnetic field. What kind of current, what kind of magnetic field you get? That depends on what kind of current that flows. Here our discussion is on static magnetic field, steady magnetic field, time invariant magnetic field. Of course, all are same. If you want time invariant magnetic field, the current should be time invariant, steady current. So, due to the flow of current in a conductor, it is surrounded by magnetic field. What kind of magnetic field? Static magnetic field. Of course, the direction of current will decide the direction of magnetic field. There is a rule, thumb rule. Thumb indicates direction of flow of current. Thumb is pointing upwards. So, if current is flowing up, look at my curly fingers like this. Fingers are curling like this. That's why, see this direction here, direction of current. The arrow is like this, means current is flowing up. So, what is the direction of magnetic field? We take like this. Thumb indicates right hand thumb rule, isn't it? You know this in magnetostatics, right hand thumb rule. I am taking my right hand, taking the right hand thumb. Thumb indicates direction of current. So, curly fingers like this. So, this is the direction of magnetic field, steady magnetic field. So, you get steady magnetic field due to time invariant current, or you get steady magnetic field due to a magnet. Because you know, if you have a magnet, it is surrounded by its own field, that is called magnetic field. Now, after discussing what is magnetic field and what is magnetic field intensity, we will move on to the second parameter, that is magnetic flux density. But well, before going to that, what are the units of this magnetic field intensity? Force experienced, force in Newton per unit north pole of how much? Of unit strength, means Weber, 1 Weber. Because pole strength is measured in terms of Webers. Unit strength means 1 Weber. So, per Weber, Newton per Weber. Or alternatively, in most of the practical cases, we use amperes per meter as a unit. And what is the symbol? Capital H bar. Because magnetic field is a vector. We use an arrow here. H bar is a symbol. Amperes per meter is the most widely used unit for magnetic field. Now, let us proceed to the second parameter, crucial parameter of magnetostatics, that is magnetic flux density. Before understanding flux density, first understand what is flux. And this is not a new thing. Flux is not a new thing. You have seen this in unit 1 in the form of electric flux. Just here you have magnetic flux and its associated extension is magnetic flux density. So, what is flux essentially? First, let us go back to unit 1 and compare with unit 2. There you have electric flux, here you have magnetic flux. Now, first, what is electric flux? If you have an electric charge is surrounded by its own field, which we say electric field. or we say electric field of that electric charge, isn't it? Electric field symbol is E bar, electric charge symbol is Q. So if you have Q, then you have E bar. Well, that electric field cannot be visually seen. You cannot see it with our eyes. But you can experience that electric field in the form of a force. That means the electric field of an electric charge can exert an electric force, because the definition of electric field is nothing but amount of electric force exerted on a unit electric charge. So what electric field can do? Electric field is capable of exerting some electric force. So you cannot see electric field visually, but you can experience the electric field in the form of electric force. And what is the direction of electric force? Which is given by Coulomb's law. Coulomb's law says that the force between two electric charges lies along the line joining the two charges. It's like this. If you have a charge here, if you have charge here, you have like this. If you have another charge here, the line force will be along this line. So this we say there is a force acting along this line. Force is acting along this line. So we say line of force. Group of such lines of force or a bunch of such lines of force is called electric flux. Similar to electric flux, if you have north pole and south pole, if you have a magnet, in place of electric lines of force, you have magnetic lines of force, which are going from north pole to south pole. Group of such magnetic lines of force is called magnetic flux, and magnetic flux per unit area is nothing but magnetic flux density. So that's what is the definition? The number of magnetic lines of force. Let us draw a neat diagram here. Let us say this is a magnet, and you have some magnetic lines of force like this going from north pole to south pole. Consider a unit surface area here. This is the area, unit surface area, which is exactly at right angles to the direction of flow of magnetic flux. So definition is the lines of force. What kind of lines of force? Magnetic lines of force, which are crossing a unit area at right angles. How many lines of force are crossing a unit area at right angles? That will tell you the quantity of or the amount of magnetic flux density. Bunch of lines of force will tell you magnetic flux in Weber, which is measured in Weber, and flux crossing a unit surface area, of course normally, that means at right angles, per unit area. Per unit area means per square meter. So that's why we have flux crossing, flux in Webers per unit area in square meters. Of course, the most practical way of using this magnetic flux density, the unit is Tesla. That means Weber per meter square is also written as Tesla. That means if the magnetic flux density is 10 Weber per square meter, then we say it as 10 Tesla, unit of magnetic flux density. Well, what is the symbol? B bar. Magnetic field is H bar, magnetic flux density is B bar. And what is the relationship between the previous parameter and this parameter? B bar equal to mu H bar. Magnetic flux density, magnetic permeability, magnetic field. That means by multiplying the permeability with magnetic field, you get magnetic flux density. So that is the relationship between magnetic field and magnetic flux density. Now, after covering two crucial parameters or the foundation parameters of magnetostatics, then we start with laws. Well, there are two important laws in magnetostatics. Number one, Biot-Savart's law, which we'll be discussing now, and number two, Ampere's circuital law. We'll continue Ampere's circuital law in the other session, but here we'll discuss the first one, which is Biot-Savart's law. Well, you can see here, Biot-Savart's law basically gives the relationship between the amount of current that is flowing in a conductor and the resulting magnetic field. Well, you know, when current flows in a conductor, it will produce magnetic field. What is the relationship between the flow of current and the resulting magnetic field? When I say relationship, it also includes what is the direction of current and what is the direction of resulting magnetic field, what is the amount of current and what is the strength of the magnetic field. When I say relationship, everything is covered. Not only the magnitude of magnetic field, but also direction of magnetic field. Everything is covered, relation means. Now, Before proceeding for this Biot-Savart's law, first we will understand a small illustration which will help us in getting the result of Biot-Savart's law. To be more specific, I can say Biot-Savart's law tells you the amount of differential magnetic field produced or measured at some point P, which is at a distance of r meters, due to a current carrying conductor, this one. That's the reason we are taking this illustration. Now first understand, P is a point at which you are measuring the differential magnetic field, due to current I flowing through this conductor. But we are measuring differential magnetic field. Differential magnetic field will be due to differential current element. What is differential current element? Current flowing through a differential element is called differential current element. Now this is the total length. This cannot be called as element. Element means which is elementary, which is the building block, which is the founding block. So don't take this entire conductor. Instead, because we are measuring not magnetic field, we are measuring differential magnetic field. So take a small section of that conductor, which we say as differential length, dl. It also considers the direction, because the direction of magnetic field depends on the direction of current, dl, and current is a scalar. So current is flowing in this differential length. The direction of differential is considered like this. And theta is the angle made by this differential length with the line joining point P and this differential length. Okay. So this is about the illustration which we are going to use for this Biot-Savart's law. Now, what Biot-Savart's law says? Look at this expression. The differential magnetic field measured at a point P is directly proportional to IDL. IDL means I means current, DL means differential length. So together IDL is nothing but differential current element. DL means differential length, I means current. So IDL is differential current element. It is proportional to IDL. Next, it is also directly proportional to sin theta. So how do you say this? The differential magnetic field is proportional to the sine of the angle between the differential length and the line joining point P and this differential length. Next, number 3. The differential magnetic field is inversely proportional to square of the distance. What is R? Square of the distance between point P and differential length. So this is, there are 3 parts included: directly proportional, inversely proportional. So to summarize, we write this equation. Next, to remove this proportionality constant, we have to take a proportionality constant, which is K. By replacing K, we get, in place of proportionality symbol, we get equality. So dH is K IDL sin theta by R square. The same thing, just we have included K. What is K? 1 by 4 pi. So dH is IDL sin theta by K is 1 by 4 pi, which is 4 pi R square. So this is the form, final form which we get. Now we can also simplify this Biot-Savart's law further, and we can also write down the Biot-Savart's law in an alternate form, which are useful in different contexts. Now how you can do that? Now I want to work on this ideal sin theta. Well, if you observe carefully, I have written here DL bar, which is ideal bar. You might be surprised. In the illustration I have written ideal bar, but here there is no ideal bar, ideal bar. Ideal bar is there, but in disguise. Inherently it is there. Now we will get it back. We will get it explicitly, ideal bar. See, try to work on this ideal sin theta. Let us see what will happen. See, you just forget about this part. Now generally DL cross AR, it is like A bar cross B bar. What is this equal to? A bar cross B bar? Mod A mod B sin theta. Isn't it? Basic expression. Now what is mod A? DL bar. Mod DL bar is DL. Mod B bar, that is AR bar, mod AR bar. What is A bar? Unit vector. What is its magnitude? Unity. Magnitude of a unit vector is unity. That is 1. So what do you get here? DL, this is 1 and this is sin theta. DL sin theta. So DL bar cross AR bar can be replaced with DL sin theta. So you have this DL sin theta here. This can be replaced with DL cross AR bar. I is there anyhow here. I is already there. I is there. Now you can replace this DL sin theta with DL bar cross A bar. Just I am writing the next step. So I is there already. In place of DL sin theta I am replacing DL bar cross AR bar. Now why I am doing all these things? Because what is this? Differential magnetic field. Whether it is differential magnetic field or magnetic field, it is a magnetic field which is fundamentally a vector. But do you find any bar here in the right hand side? There is no bar. But inherently it is there. So we have to get it outside, the vector nature. That's why I am doing all these things. Now, I DL cross AR bar by 4 pi R square. This is same as it is previous case. Next, we can simplify it further, even further. How? You have here A bar R. What is A bar? It's a unit vector. What is its definition? A bar is equal to A bar by mod A bar. Isn't it? A bar by mod A bar. But here you have A bar R. Means this is a unit vector which is defined for R. So that's why AR bar is R bar by mod R bar. R bar, mod R bar is nothing but R. So wherever you have AR bar, replace it with R bar by R. So where you have AR, here you have. That is equal to R bar by mod R. This R goes to the denominator. Already you have R square. If it goes to denominator, it will become R cube. And this R bar goes into the numerator. That's what I did here. So in the denominator, in place of 4 pi R square, you get 4 pi R cube. In place of AR, in the numerator, you get R bar, which is R bar. This thing will remain same as it is. This will be same as it is. So this is one form. By simplifying this, using this expression, we get this. Now there is one more way of making a final result. Till now we have been writing the expression for differential magnetic field, because Biot law deals with the amount of differential magnetic field measured at point P due to a differential current element. What if you want the magnetic field itself, not differential magnetic field, the magnetic field itself? If you know differential length, how do you get total length? By integrating differential length, you get total length. If you have differential magnetic field, how do you get total magnetic field? Just integrate differential magnetic field, you get total magnetic field. That's what I did here. Till now I have written DH, differential magnetic field, but now I am writing magnetic field. How do you get magnetic field? The magnetic field is obtained by integral of or integrating the differential magnetic field. This entire thing you see inside the integral is nothing but differential magnetic field, isn't it? This is the same expression what you find here. H bar is integral DH bar. By integrating differential magnetic field, you get magnetic field. What is DH? This is DH. This entire thing I am substituting here inside the integral. IDL cross AR by 4 pi R square. 4 pi R square. There is an integral. But if you find a difference, I have kept a circle for this integral. What is the meaning of that? If this is called integral, this is called closed contour integral. We are integrating throughout the length. This is line integral, single integral. Mathematically, it is single integral or line integral. We have taken this closed path. Closed path indicates it is an integral performed on a closed path, closed contour integral. Why? Because you are finding out magnetic field due to the flow of electric current, isn't it? Due to the flow of electric current only, it is surrounded by magnetic field, and we are analyzing that magnetic field using Biot law. Now, can current flow in an open path? Current can flow only in a closed path. We say current flowing in a circuit, isn't it? What is circuit? Circuit is a closed path. So, I have taken this closed contour symbol. That is the meaning of this. So, this is all about the Biot law, which is the first significant law in magnetostatics. Then we have one more law, which is Ampere's circuit law. which will be discussed in subsequent sessions.